Hey everyone, and welcome. Today, we're going to peel back the curtain on the tech that pretty much powers everything you do online. We're talking about distributed systems. They're like the invisible architecture holding up our entire digital world. So let's just dive right in.
Seriously, just think about that for a second. How on earth can a service like Netflix or YouTube or even your bank handle millions of people all hitting it at once from all over the globe? Well, the answer? It lies in this powerful, kind of complex, but really fascinating world of distributed systems.
Okay, so to kick things off, we're going to start right at the beginning. Let's really unpack what a distributed system even is, and maybe more importantly, why we would ever go through the trouble of building one in the first place.
Now, this definition is absolutely key. A distributed system is a bunch of independent computers, right? But the real magic word here is appear. The entire goal, the whole trick, is to create this seamless illusion that you're just dealing with one single, incredibly powerful machine.
So why do we do it? Why go through all that hassle? Well, these are the big reasons, and they're super practical. First up, economics. It's just way cheaper to link up a bunch of normal computers than to buy one giant mainframe. Then there's speed. More computers means more horsepower, simple as that. Some apps are just naturally spread out, so they have to be distributed. And this is a huge one, reliability. If one machine in the network goes down, the others just pick up the slack, and you, the user, never even notice. And finally, you can grow incrementally. Need more power? Just add another machine to the pile. Easy.
All right, so now that we've got a handle on the what and the why, let's actually take a look under the hood. We're going to move away from the abstract ideas and look at some real, concrete examples you use every single day.
And here it is, the ultimate distributed system. The internet itself. I mean, it's this massive, sprawling collection of servers and computers and networks all talking to each other. When you open a web browser, you're not connecting to a single box somewhere. Nope, you're interacting with a tiny piece of this gigantic global web.
But these systems aren't always global. You can scale it way down. Think a typical corporate intranet like you'd find in any office. You've got file servers, printers, desktop computers, all hooked up on a local network. There's still a bunch of independent machines working together, just on a much smaller scale than the entire planet. So how does all this actually work? Well, you can think of it like it's built in layers. At the very bottom, you have the physical hardware, the actual computers and wires. On top of that, each machine runs its own operating system. Now here's the secret sauce, the middleware. This is the special software that acts like the glue, connecting everything and creating that single system illusion we talked about. And then, on top of all that, you have the platform, and finally, the actual applications you use, like your email or Netflix. Now, this all sounds pretty great in theory, but in the real world, building and managing these systems is, well, it's incredibly hard. So let's talk about some of the massive challenges that engineers are constantly wrestling with. Okay, the first big challenge is something called heterogeneity. And that's really just a fancy word for everything is different. You've got different networks, different computer hardware, some machines running Windows, others Linux, code written in a dozen different languages. It's like trying to get an orchestra to play a symphony when every musician has a completely different instrument and sheet music. Making it all work together is a monumental task.
All right, next up, scalability. The big question here is simple. As you add more and more users, can your system actually keep up, or will it just grind to a halt? The absolute biggest enemy of scalability is any kind of bottleneck. If you have one single file that everyone needs to access, or one server trying to do all the work, you've created a choke point that's just bound to fail as you grow.
Now, this is a really unique problem for distributed systems, partial failure. See, your laptop either works or it doesn't, but in a distributed system, one piece can crash while everything else keeps on running. So the challenge is, how do you even detect that failure, hide it from the user, and recover gracefully? A really cool technique for this is replication. For instance, the space shuttle literally had 3 identical computers running the same software. If one of them gave a different answer, the other 2 would outvote it. That is failure handling in action.
Okay, quick thought experiment for you. Imagine a bank account with exactly $100 in it. Now, at the exact same time, you deposit $50 from one ATM and a friend withdraws $30 from another. What's the final balance? Take a second to think about it.
The right answer, of course, is $120. But it's shockingly easy for a system to mess this up. What if both ATMs read the starting balance of $100? One adds 50 and thinks the new balance is 150. The other subtracts 30 and thinks it's 70. Now what? Who wins? This whole mess is the challenge of concurrency.
making sure that when lots of people are using the same thing at once, the data stays correct and consistent.
So with all these insane challenges, making different things work together, handling failures, dealing with concurrency, how do we ever make these systems usable for normal people? Well, the answer lies in a really important concept called transparency. It's the magic trick that hides all that complexity from us. So this is the big definition you want to remember. Transparency is all about hiding the messy reality. The whole point is to make a system that's spread across who knows how many machines, maybe even across continents, feel like it's running right here on your own computer. And there are all kinds of transparency. A good system can hide where a file is physically located. Is it in London or Tokyo? Who cares? It can hide the fact that a file might be moving from one server to another. It hides that there are multiple copies of your data for safety. And it hides the fact that thousands of other people are using the exact same resource at the exact same time as you. But, and this is a big but, perfect transparency is a myth. It's impossible. You simply can't hide the laws of physics. It takes time for a signal to cross an ocean, and you'll always feel that delay. It's also impossible to know for sure if a server is just being really slow or if it's completely crashed. And ironically, trying too hard to hide everything can actually slow the whole system down. This picture is a perfect example of why this is all so hard. A user makes what feels like a simple request. Show me this report. But behind the scenes, to build that report, the system might have to pull data from a server in Paris, another one in Montreal, and a third in Boston, all over the network, just to answer that one question. Hiding that chaotic dance is the constant struggle. Okay, in our final section, we're going to look at one last critical challenge: security. And some really dangerous false assumptions that developers can fall into when they're building these systems. Security is obviously a massive concern. You've got a few main pillars. Confidentiality is about keeping your data secret from anyone snooping. Integrity means making sure nobody's changing your data without permission. Authentication is just proving you are who you say you are, like with a password. And authorization is checking if you actually have the right to do what you're trying to do.
And finally, we get to what some people call the 7 deadly sins of designing these systems. These are all false assumptions that are so easy to make. Believing the network is always reliable, or totally secure, or that there's no delay. Making any of these assumptions leads to brittle systems that just shatter in the real world. You have to build things with the expectation that things will go wrong.
And that leaves us with one last kind of mind-bending question to think about. We build these systems so they don't have a single point of failure, to make them reliable. But if a system is truly decentralized, does that also mean there's no single point of control? It's a pretty fascinating idea when you start thinking about the nature of the internet itself. Thanks for joining me for this explainer.